All right, so let's work through a couple examples of hypothesis tests for one proportion. Now, we're going to be using our TI Inspire to do the heavy lifting. I'm also going to show you how the formulas work, but mostly TI Inspire here. Remember, we're going to use that acronym PHANTOMS to do this with, to help us keep track of all of the pieces. So, research indicates that 10% of all people are left-handed. A study of 1,650 people randomly chosen from the population age 65 and older contained only 133 lefties. Does this data provide evidence that the proportion of elderly people who are left-handed is smaller than the proportion in the general population? Now, as I'm reading through a hypothesis test question, and I don't really know it's a hypothesis test yet, I'm looking for a couple of keywords. In this case, you'll see I have it highlighted in green. It says, does this data provide evidence? Okay, so if I'm supposed to be providing evidence, it's like I'm like strapping on my district attorney coat and I'm saying, okay, I'm going to run a test. I'm going to look for evidence. Okay, I'm trying to test. So I'm in that guilty, not guilty idea, which means I'm going to be running a hypothesis test. Remember, for a confidence interval, one of the things we were looking for was that phrase, estimate or find an estimate with or something like that, approximately what value. So we were looking for actual numbers. This data is we're looking for evidence for something. The other thing that I note in this problem that kind of keys me in that I may be doing a hypothesis test is the inequality words. I'm looking for smaller than, because I know when I write my alternate hypothesis, I have to put an inequality in there. So this idea of smaller than, all right, smaller than, that's going to be a less than. So I know I'm going to write something is less than something else. All right. The other thing I note in here is that there's no alpha level stated, so I'm just going to assume that I'm going to use about 5%. A lot of times if you're working a problem and there's no alpha stated, it's because the person who wrote the problem knows that the end result is either going to be so small that it doesn't matter where you set your alpha, or so large that it doesn't matter where you set your alpha. It would be really weird if they didn't state the alpha level and your alpha ends up being like 5.1% or 4.9% or 3% or something like that. Okay, so I'm going to start off with phantoms. So P is the proportion of. Now, I know when I go to write my hypotheses, I want the proportion is going to be that P is smaller than something else. So if I look right in front of that, the proportion of elderly people who are left-handed, I'm just going to mimic the stem and write that. So I'm going to say the proportion of all elderly people who are left-handed. And I'm going to try to write this in present tense or future tense and not past tense. I'm not going to say who were left-handed because that sounds like the sample, and I want this to be for everyone. All right, my hypotheses then. I'm going to have the HO and the HA. They're both going to be P's because we're talking about a test for proportions here. And it says smaller than the proportion in the general population. So we're talking about the proportion of elderly compared to the proportion of everyone. And the problem tells us that 10% of all people are left-handed. So equals 10% would be the same as the general population, and less than 10% would be smaller than the general population. Now, what I have written in red right here, you don't have to write that, but sometimes I'll do that for myself because that helps me later interpret what's going on and really understand what I'm doing. If I'm trying to put this in context. All right, so I'm going to check my conditions. So the first condition is a random sample or random assignment. So do I have a random sample? Yes, it's stated in the problem that they randomly sampled these people. So randomly sampled, that is stated, check mark. Okay, is the 10% condition satisfied? So 1650 was our sample size. Is that less than 10% of? Now, the population we're taking the population proportion of is all elderly people, so that's what I'm going to use for that. And that is totally reasonable, moving on. The next thing I want to check is, do I have a large enough count that I can say a normal model is appropriate for this problem? So 1650 was my sample size, and I want to take n times p. In this case, we're going to use the hypothesized proportion, 10%, instead of the p hat value, which would be the 133 out of 1650. I'm not going to use that number. I'm going to use this because if you know p, you should use p. So 10% of 1650 is 165. That's definitely greater than or equal to 10. And then 10% minus, 100% minus 10% is 90. That's 1485. Definitely greater than 10%. So yes, the sampling distribution of p hat would be approximately normal if this p is 10% is true. So we're going to use the hypothesized value for this check, not p hat like we did with confidence intervals. All right, so name that test. So that is going to be a one sample z-test for, and I would encourage you to write population proportion here. I didn't do that in the notes, but I really should have. Okay, one sample z-test for population proportion. Okay, the next thing I need to do is I need to find the test statistic and obtain the p-value. All right, now I'm going to go ahead and run this in my TI Inspire. So here's how it works. I'm going to pick up my TI Inspire here. Here we go. I'm just going to go to a plain old ordinary scratch pad. Maybe. There. Oh. Hit it too many times. All right, and I'm going to go menu, statistics, and the one I want is number 7, stat tests. And then I want to run a one proportion z test, a one sample z test for proportion. All right, so I run that one proportion z test. I'm going to hit this and it's going to say, what is p sub 0? In other words, what is the proportion from the null hypothesis? So I'm going to say that was 10%. All right, the number of successes was 133. And the sample size was 1650. Now, it defaults to an alternate hypothesis of not equal to, but I want to pick less than because that's how we set up our alternative hypothesis. We want to know if the proportion is less than the general population, less than 10%. That's it. I'm going to hit enter, and I get this delightful, here's z, negative 2.626. Okay, probably use at least 2 or 3 decimal places for that. And then the p-value, which is the probability of getting a z-score of this or more extreme, is 0.00432, about 0.004. Notice it also gives us p hat in this report, which would be 133 out of 1650, and reiterates that in sample size there. All right, so back to my paper. By the calculator, I get these answers. I am literally just going to write them down. Z equals negative 2.626 and p-value 0.004. Okay, I copied them from my calculator. Boop. Okay, now if you were going to do this with the formula, here's how it works. I'm calculating a z-score. The test statistic, it's a z-test, so I'm going to calculate a test statistic of z. So I'm going to take the statistic, which is the number from the sample, p hat, 133 out of 1650, minus the parameter, which was p, 10%, divided by the standard error of the statistic. Now, I have two values that could potentially go in for p here, the 133 out of 1650, which was about 8%, or this 10%, which was the hypothesized proportion. So if I have to pick between the two, I'm assuming that p is the true number, so I'm going to use that in my formula instead. So in general, if you have to pick between p and p hat, always pick p. Okay, always pick p. So my p is p times 1 minus p over n from that standard deviation formula, square root. If I pop this in my TI Inspire, I get negative 2.626. Now, when you do this, make sure that you put parentheses around this or use that stacked fraction. Okay, so if I did want to, oh, there's my videos, wrong one. Okay, if I do want to do this as that stacked fraction, I would press Control and division, and then I could do 133 divided by 1650 minus 10%, and then I'm going to tab down to the denominator there. I'm going to do a square root of 10% times 90% divided by 1650. Okay, and there's that negative 2.626 value. All right, so the p-value, to get that, I would think, well, this is a z distribution, right? So I've got z here, standard normal distribution. That means I have a normal distribution with a mean of 0 and a standard deviation of 1. Z-score of negative 2.626 would be over here somewhere, and I would want the area to the left because I want the area in the tail, the extreme values. So to compute this in my TI Inspire, I would do a normal curve probability. So menu, statistics, and distributions, and I want number 2, norm CDF. I love this because it defaults to negative infinity, which I need. I'm going to type in my z-score, negative 2.626. It defaults to 0 and 1, which is great because I'm working with the z-score anyway. So I put OK, and there's that probability, that p-value. Okay. Now, for sake of time, I would recommend that you know how to do these things. This is important. But in this time crunch we are in the end of the year, it's also, you can just pull these out of your calculator and write them down. Okay. Okay. So make a decision. I'm going to use an alpha of 0.05. Our p-value is really small. So I could have set this at 1%. It would have been still fine. 0.0043, it's less than or equal to 5%. So since that p-value is low, I'm going to reject the null hypothesis. P-value low, reject ho. Okay. So Here's my conclusion. The first statement is going to be about the null hypothesis. I'm going to reiterate that, make a decision in a complete sentence. Since the p-value is less than alpha, and I've stated what alpha I used up here since they didn't state it, I reject the null hypothesis. Now, if you're in a class that doesn't want you to use first person pronouns like I or we or things like that, go ahead and say, since the p-value is less than or equal to alpha, the null hypothesis is rejected. Okay. There is convincing evidence. So we said guilty, so we had good evidence. Okay, there is convincing evidence that the proportion of elderly people who are left-handed is smaller than 10%, the proportion in the general population. Okay, so that's we have evidence for ha, but we write that in context. Okay, so here we go. All right, here's another example. A union spokesperson claims that 75% of union members will support a strike if their basic demands are not met. A company negotiator is concerned that the true percentage is higher than 75% based on a simple random sample of 125 union workers, of which 98 said they would strike. Is this strong enough evidence? Ooh, there's those buzzwords that tells me I want to do a hypothesis test. That the true proportion of union members who will strike is greater than 75%. And again here, no alpha is stated, so I'm going to go ahead and say 5% for that. All right, so I see this inequality statement here. Is it higher than 75%? Is it greater than 75%? So there's my inequality word that I know I'm going to be using for my alternate hypothesis. And I know in the alternate hypothesis that I'm going to have something in front of it. What parameter is greater than? So I'm going to look in front of that word, and it says the true proportion of union members who will strike. That's what I'm going to use as my parameter definition. All right, so P, define the parameter. P is the true proportion of union members who will strike. My hypotheses are going to be the null hypothesis is that it is 75%, and the alternative hypothesis is that it's going to be greater than 75%. I'm going to check my conditions here. It does state in the problem that he does an SRS. So this is a random sample because a simple random sample was stated. 125 is less than 10% of all union workers. There's that 10% condition. Okay, I have no idea how many union workers are in this company. So I'm just going to say, assume this is reasonable. Now, if that really makes you nervous and you're in a problem that makes you uncomfortable about saying that, you could say, assume it's reasonable and proceed with caution. All right, I need to check to see if we have a normal model is appropriate. So again, I've got the P hat number, which is the 98 out of 125, or I've got the P hypothesized proportion number, which is 75%. If you're picking between a P and a P hat, always pick the P for the formula. So I'm going to do N times P. 125 times 75% is 94. That's bigger than 10. 125 times 0.25, that's 31. That's bigger than 10, which tells me that my sampling distribution of P hat is approximately normal. So we are good to go. Just a word of caution here. Be careful that you don't try to pop central limit theorem into this. Central limit theorem is the one where we say the sample size is bigger than 30. That only works for a sampling distribution for means and never one for proportions. Okay, so be careful with that. This is a one sample Z test for a population proportion. All right, so we're going to write that down, literally one sample Z test for population proportion. Now, I'm going to run this in my calculator, or I can do this by hand. So if we were going to run this in our TI Inspire here, let me get these numbers into my brain, 75%, 98, and 125. So I would take, and I'm going to clue this out really quick, Doc B will clear your screen on your scratch pad. I'm going to go menu, statistics, and stat tests. And again, I want the one sample Z test for proportion, which is number 5. We had 75, and the number of successes was 98, I believe, but now I've forgotten. 98, yes. And then 125. And again, this is going to default down here to not equal to. We want to change it to greater than. Hit OK. My Z-score is 0.88 or 0.878-ish, and my p-value is about 19%. All right, so my Z-score 0.8779 rounded, p-value is 0.1900. Now again, to do this by hand, you would take the statistic minus the parameter, divide by the standard error. You're going to use the p equals 0.75 from the null hypothesis instead of the p hat in that standard error, standard deviation formula. You get that same value, and then you would use a norm CDF going from the Z-score up to the infinity with a mean of 0 and a standard deviation 1 to get that same probability. Okay, so you can do this by hand, absolutely. Okay, but you can also just write them down from your calculator. All right, now to make a decision, I'm looking at this at an alpha of 5% here. The p-value, yeah, that p-value is pretty big, 19%, that's greater than that. So p-value not low, I am not going to reject, I'm going to fail to reject. Now I'm going to write that in a complete sentence then. Since the p-value is greater than alpha, and I've already stated what alpha is up here, I fail to reject the null hypothesis. Fail to reject the null hypothesis, period. So this is like saying not guilty. Not guilty. I failed in my job as the district attorney. I failed. I did not provide convincing evidence to the jury, so that's how I'm going to start that. There is not convincing evidence that, alternate hypothesis, I haven't provided convincing evidence of guilt. That is, I'm going to go back and look at it again. P is greater than 0.75. P is the true proportion of union members who will strike. I'm going to write that down. The true proportion of union members who will strike is greater than 75%. Now, this does not prove that it is 75%. This just says that it's not greater than 75%. I haven't shown evidence that it's greater. It still might be greater, just my evidence is not stronger than that. I don't have convincing evidence of this. So we got to be real careful with that conclusion. Okay, last one. A report states that nationwide, 61% of high school graduates go on to attend a 2-year or 4-year college the year after graduation. Suppose a random sample of 1,500 high school graduates from Indiana estimated the proportion of high school graduates that attend college the year after graduation to be 58%. Can we reasonably conclude that the proportion of Indiana's high school graduates who attend college the year after graduation, whew, that's a mouthful, is different from the national figure? Use an alpha of 0.01. Okay, so a couple of things here. I see nationwide all high school graduates, and then I see a sample of 1,500 from Indiana, and that number was 58%. So the number from the sample is 58%, which means we're probably going to use this 61% here as our population parameter hypothesized proportion. So remember, the sample gives you the statistic, which is going to be that 58%. The other thing I noticed, it says different from. So that'd be different from either way. Like, is our number different either way from the national average? Normally, you would determine this before you go and take your sample, by the way. So what is different than? The true proportion of Indiana's high school graduates who attend college the year after graduation, or who would attend college, or who will attend college. We want to make sure we're putting that in that future tense or present tense there. Okay, so I'm going to write this two-tail test P. Okay, I'm going to use that population parameter, not the sample statistic. Be careful with this. Is going to be equal to 0.61 or not equal to 0.61 in that two-tailed test. All right. The random sample is stated, I believe. Random sample is stated. Is 1,500 less than or equal to 10% of all Indiana high school graduates? That is reasonable. I mean, our high school has like 3,000, so that's, very reasonable. And then I'm going to check my N times P's to see if my model is appropriate. So I remember I'm using the P, not P hat in this. 0.61 and 0.39 times 1,500 give me results that are plenty bigger than 10. Those counts are definitely large enough, so the sampling distribution is approximately normal. This is going to be a one sample z-test for a proportion, for a population proportion. So we are going to need to find the z-score for this z-test. Now again, I would do this in my calculator, but I have to be a little bit careful if I'm going to do this in my calculator. The calculator requires that I enter x, the number of successes. So 58% is the proportion of successes, but there's nowhere to type that in my calculator. So when I go to put x in, I need to think 58% times 1,500, and I need to make sure it's a whole number. So, for example, we don't really have an issue here because when I take 58% of 1,500, I end up with a nice whole number, 870. But if they had said 59% of 1,500, let's see if that'll work. Oh, I got a whole number with that too. Maybe it's because of the 1,500. Let me try again. 0.59583. So I've got some other number here that is this one? There we go. That's not a whole number. If that's what I had, if that's what my percentage of my problem, I would need to put in a whole number. If I try to type in 893 blah, blah, blah into my calculator is going to freak out and say, domain error, you can't do this. It's not going to run your report. And that actually people have had problems with that before. So we would want to type in 894 here, 894. Okay. But actually we're going to type in 870 because that's the one we want. All right. So menu, statistics, statistics tests. We want a 1 proportion Z test. It was 61% was the claim. We have 870 out of 1,500, and it defaults to not equal to. That's the one we want. Hit enter, and I end up with a Z-score of about negative 2.38 and a p-value of about 1.7%. All right, so I'm going to go back. There's my Z, there's the p. Now, this is actually a nice one to do by hand because they give you the statistic as a percentage. So we're talking about 58% minus 61 divided by the standard deviation using the hypothesized value, not the p-hat value. Get the same Z-score, but you want to be really careful when you compute this distribution. So you're going to sketch a two-tailed test. So this negative 2.382, that is the left bound, but you also want to do the right side as well because different than implies less than or greater than. So I'm going to find the area to the left. So I did a norm CDF from negative infinity up to negative 2.3-ish and got about 0.008. And then that's going to be the same on the other side. So I just doubled it. So that's where that 0.017 is coming from that we got before. Okay. Now this p-value is greater than 1%. Remember it was set for us 1% this time. If we had set it ourselves at 5%, that would give us a different result here. And that's important to note. So, this is greater than alpha, so we're going to fail to reject. So since the p-value is greater than alpha, I fail to reject the null hypothesis. This is like saying not guilty. So there's not convincing evidence that the true proportion of Indiana's high school grads who attend college year after graduation is different from the national average. Now, questions. What if I had used 5% instead of 1%? If we'd used 5%, the p-value would have been less than, so we would have rejected and said there is convincing evidence that it's less. Or it's different if we're talking about a 5% chance instead of a 1% chance. Okay, so why would you want to use a very small alpha level? So why would we want 0.01 versus 0.05? And basically that depends on the seriousness of your test. So if you're testing something that you really can't afford to be wrong about this decision, you need to be really, 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 really sure. Okay, that would give you a reason to put a small alpha level. However, the other thing about that is the larger your alpha level is, the better the chance you have of disproving that claim and going with that alternate hypothesis. And we'll talk about that in the next section. Another thing is, what if we had said less than instead of not equal to? So if we had said less than and just had a left tail test, we wouldn't have doubled this area on either side of the normal curve, and we would have had a 0.008, which would have been less than alpha of 0.01, which would have caused us to reject and say we do have evidence to support the claim that it's less than. However, when you're doing a hypothesis test, you need to come up with a claim to begin with. And before you go out and take your sample, you need to decide what you're testing for. Otherwise, it's kind of like they said in the AP Classroom videos, it's kind of like cheating. Okay, so you want to make sure you test that claim after. All right, if you have any questions, please let me know.